anybody have any questions about anything or anything we've done so far? Anything else? Nothing?
Remember the last one on the homework.
All right, can you tell me what it is?
Was it 3.1? What? 3.1?
It was 3.16.
3.6.
3.16, 362.
Says you were given two Z-directed line charges of charge density plus one.
1 nanocoulomb or 1 coulomb?
Yeah, nano.
Nanocoulomb
Per meter.
located?
At x equals 0 and
Wait, so X, all this Y, and Z. X equals 0?
x equals 0, y equals -1.
All right, so this is -1. That's an infinite line charge, so it's in the Z direction. When they give you the coordinates of X and Y, you know the other coordinate is the one that's infinite.
And charge density.
This is rho L equals 1 nanocoulomb per meter cube, meter squared, meter per meter, right? That's positive, right?
For charge density is plus 1, yeah.
All right. And then there's 1 at plus 1,
Yeah,
and this is going to be negative minus rho L. Or it's actually going to be minus 1 nanocoulomb per meter, is that right?
mm-hmm.
All right. For this
At
one,
0 and positive 1 for y. For x
it's
0.
y equals 1, or it was x equals 0, y equals 1, right? So it's infinite in the z direction. Now, the way I'm going to suggest you do these kind of problems is look down the actual infinite axis. Make them look like points. I know that if I have an infinite line charge with charge density rho L and I'm a distance rho away, we'll get to, we did cylindrical coordinates, we'll do spherical today. Rho is just the radial distance from the z-axis to the point of observation. Then I know that the electric field at this point is in the radial direction, pointing away from the axis, and it's equal to the charge density, rho L, over 2 pi epsilon naught rho, and it's in the arrow direction. The arrow direction means it's pointing away from that infinite line of charge. Follow me? All right, now when I do this problem, what I'm going to do is cut this plane right through the xy plane and look down the z-axis, so it'll look like this. Now, this is going to be my x, and this will be, actually, let me do it this way. I'll make this x and make this y, and I know at y equals -1, I have plus. So right here, I'm going to have a charge density of plus rho L, and we'll just say rho L. Here is 1 nanocoulomb per meter. And here, it's -1. At a height of 1, I have plus rho L, right? And now he wants the electric field at a point. What point does he want it at? X equals what?
1.
1? So he wants the electric field right here at 1. You all see this? Now I'm looking down the z-axis. That's important. I know that I know the electric field will be of this form. And here, a rho means it's pointing away from that axis that causes it. And this becomes critical. Now, I want you to write this down right here. It's not stated explicitly in the book. What a rho really is, all right, that vector is going to be whatever rho is, vector rho, over the magnitude of vector rho. Now, rho here just means the distance from this point to this point. What, with me on this, class? I know in cylindrical coordinates, we get used to thinking of as this always being on the z-axis, so rho is just going to be a measurement from the z-axis. But the real definition of rho, it's from the axis of the charge, in this case, to the point of observation. So just watch what I'm doing here. Now I see this charge, this has got a positive charge, this is a minus charge density, right? Minus rho L. So this one, if I draw a line through here, I can graphically see that the electric field from this one will be in that direction. Does that make sense to everybody? It'll be radially away. Because this is a negative charge, the electric field will be pointing to it. You all see that? Everybody? It points towards the negative, away from the positive charge. Are you all with me on this one, class? Now, something else, when you sketch these things, you get to see, because the magnitude of these two charge densities is the same, the magnitude of this Z field component and this Z field component will be the same as well. Do you all see that? Can you appreciate that? It's good to make sketches. And what do you see happening? Do you see how the horizontal components are going to cancel? And the vertical components are going to add. Do you agree with me? Now, just to do this for completeness, I'll call the electric field from this charge, I'll just label this charge density 1 and this charge density 2. So I'm going to label E1 right here. And that's going to be rho L, that's a scalar value, in this case 1 nanocoulomb per meter, over 2 pi epsilon naught. And then I have to get a vector rho. Now this is important, you see this. The distance from here to here is my vector rho. And that vector rho would be what? Well, anytime we're talking about a vector between, a distance between 2 points, it's a vector. You always take the coordinates of the point of observation minus the coordinates of the actual, charge, and subtract them. So for this one, the x coordinate would be 1 minus 0. Do you agree with that? X coordinate here is 0, x coordinate here is 1. That's the point of observation. Agreed? So it's going to be 1ax, or just ax. The y difference is what? Well, this y value is 0, correct? That's the point of observation. This y0 is minus 1, correct? So it's 0 minus a minus 1, or plus 1ay. You all see this, class? Now the magnitude of that is what?
Square root of 1 squared plus 1 squared.
Or square root of 2, correct? That means a unit vector, call it a rho that I'm putting here. A rho is actually going to be rho vector over magnitude of rho, or a rho is going to be equal to ax plus ay over the square root of 2. Do you all agree with this? Yes.
Don't you need to take into account the z direction as well?
It's infinite in the z-axis, right?
Yes.
If this z point was different than this z point, then we would. But because it's infinite in the z direction, the electric field will have no component in the z direction. Remember, infinite in the z direction, right? All fields point radially away from the axis, and that would be in the xy direction. But the fact is this, if this was a point charge and we wanted something where it wasn't at the same value of z, then we would have to take the difference in z, but perhaps that's true. Okay. Now for this, now I come down to this. This is divided by magnitude of rho. Well, the magnitude of rho here is going to be what? Just square root of 2, right? So I can put down square root of 2, and then I have to multiply it by a rho. Like I showed over there. And a rho is going to be quantity ax plus ay divided by the square root of 2 also, right? So I can write this E1 here as rho L is 10 to the minus 9th over 2 pi. And you can write epsilon naught as 1 over 36 pi times 10 to the minus 9th. I'll just tell you, epsilon naught can be rendered as 1 over 36 pi times 10 to the minus 9th farads per meter, or epsilon naught, if you do the math on this, is 8.85454 times 10 to the minus 12 farads per meter. Either one's acceptable, but the 1 over 36 pi allows a lot of cancellations. 36 pi times 10 to the minus 9th here. Then square root of 2 times square root of 2 is just 2. And then I have ax plus ay. Magnitude in x and y direction is the same. That means E1 in this thing, just look at this for a second. You see how nice everything cancels? I got 10 to the minus 9, 10 to the minus 9, gone, right? I mean, you all see it, right? Then I have 2 pi into 36 pi, right? Pi's go away, 1 over 36 is 18, right? Correct, class? I have, and so that means I have 1 over 18, but it's I have 2 there, so it's really 1 over 9, don't I, class? Then I take that, put it upstairs, so that means I have 9ax plus AY. That would be E1. Does everybody see this? And that would be volts per meter, by the way. I just want to make sure you see the math. We can exploit symmetry in a second, but and we will, because then when we exploit symmetry, the only thing we're going to take is what? We're going to take into account the AY component and simply double it from that one. We're going to see the AX.
Look at the square of the distance.
Well, it's magnitude of rho down here, isn't it?
Yeah.
Well, if that's magnitude of rho, it's square root, isn't it? Of 2?
It's magnitude of rho squared. Is
No, it's 1 over rho. Take a look. Do you have your books?
The point charges.
Those are point charges.
To each other for the line charges.
Point charges are 1 over 4 pi epsilon naught over r squared. Line charges, it's 1 over rho, 1 over the distance.
okay.
All right, now we come down to this, so that's 9 volts per meter in the AX and AY direction. Take a look at E2, that's from this one. This is E2 right here, and it's pointing in this direction. Do y'all see that? You realize they're identical magnitudes, everybody? The only difference is the direction for the AX component is now negative. Do y'all see that? So literally I can say that E2, without doing the math, and I could do the math, but it's going to be a repeat, is just going to be 9 times, then it would be minus AX plus AY, volts per meter. Does everybody see that? What happens when you add these two up for E total? What do you get? E1 plus E2 is equal to, just look at it. It's going to be simply going to be what? 9, right? AY plus 9AY or 18 AY volts per meter. Is that what the answer is? AY volts per meter. Is that what it is?
Yeah.
Now, I'm going to tell you, the 1 over 36 pi is a nice little trick there to use for epsilon naught. 1 over 36 pi times 10 to the minus 9, because there's a lot of cancellations of the pi's and stuff. Yeah.
In the book, it says that 1 over 36 pi can also be 8.85 to the negative 12.
That's right up there. See it?
Yeah.
8.854 times 10 to the minus 12.
Okay, so would you prefer us to use the 36 pi?
Well,
It's easier?
the answers are going to come out about the same. I'm just going to tell you, I mean, you can use 8.854 times 10 to the minus 12. As a matter of fact, some of your calculators will have epsilon naught in the memory. They'll have Planck's constant, Boltzmann's constant, epsilon naught, mu naught, and a whole lot of others. C, the velocity of light, built in there as constants, the high order of precision. Does anybody have this in your calculator? Do you have scientific calculators? Don't they have constants like pi's in there? Isn't pi 3.14156? It's a repeating decimal.
Yeah.
And then there's pi, there should be, if you look in the actual manual, you'll probably see constants. Planck's, Boltzmann's, Avogadro's number, epsilon naught, mu naught. I can't think of all of them, but most scientific calculators have that in memory, or you can buy a card and get it. Frankly. Any other question about this? Any other questions about the homework?
I don't have a question about the homework, but I had a question about something that was in the book. I was
Go
just
ahead.
wondering how you solved it.
Go ahead.
It isn't really an explanation, it's just a picture, so I was.
All right, let me, I gotta find these erasers. Gross, I think, takes everything and hides it. He is a neat freak. Anybody see what the eraser is?
I don't think we had one for this classroom. I don't think there was
We
one
did, it's
here
gone.
last
So I just
semester.
went downstairs.
Don't worry about it, I got this rag, but, you want me to take a look at something?
Yeah,
Is this the bounce diagram?
yeah, but it's like the 2 diagrams.
Yeah, what he's doing for this one is, he wants a pulse, it's got a finite duration. So, let me just comment on this. This is a pulse that isn't just a battery that's held there. What page is that in the book?
This is page 892,
All right, if you have a book, turn to page 892.
or sorry, just 92.
92.
Eight.
892 will be a little better.
Yeah, just what exactly it says canceling out and stuff.
now here's what he's doing for this. The bounce diagram stuff's important, but he says, I want to know what happens to a transmission line like this with a given load, RL, and it's got a given Z naught here. And now what I'm going to do is have, there's some RS here, but instead of an actual just a battery here, I have plus to minus a voltage source, and the voltage source has a value like this. It goes up to some value, call it V naught. It stays there for a time tau, and then it goes to 0, and this is time, and what he wants to know is what the voltage is at the load or some other point for that pulse. Well, here's how we make this pulse work. We say this pulse right here can be rendered like this. If I have a battery of V naught here, and I have a switch right here that turns down at t equals 0, right? And that would start it, right? Correct? Then what I want to do is this. I'm going to take this and I'm going to find the voltage on the transmission line for this source. And then I'm going to add to this. This would be the actual voltage source that we go here. I'm going to add to it this. This is going to be a voltage like this. It's going to be plus to minus opposite polarity V naught. Here's the switch. It goes down at t equals 0. But I mean, not t equals 0, it goes down at t equal tau. Now, hear me on this one. This is like a constant voltage floating there, and you can get the bounce diagram at any point, right? We can get the voltage for this one. Do y'all agree with me? Now what we do is, we do a time delay, and we say this one is going to have the exact same bounce characteristics, except they're negative and they're time delayed by tau. So the way we do this, and he shows this on this graph, and I'm not sure how, he probably uses different colors. He takes this as time going down, and now, does he do the voltage at the load or where?
Yeah, I think it's
Well,
the initial voltage.
Here's what you do. You start out and you get your V prime at t equals 0. This would be V prime. And V prime, of course, would be what? That would be Vs or V naught. V naught in this case. And it's going to be times Z naught over Z naught plus Rs. Do y'all see that? That's the voltage just on the inside of this transmission line. So we get V prime here, and we do our little bounce. Bang, bang, bang. And there's a gamma L here, and there's a gamma source here. And we go ahead and draw a little bounce thing, like so. And then, if I had a different colored marker, it would be a little nicer, but I don't think I do.
I don't know, I don't know if it works, though, you can try it.
Is that what, that's erasable, isn't it?
Yes, that's fine. Should be good.
Then, he comes down to the point tau.
All right.
That's a good try. Good try. He comes down to the point tau, right? This is the time delayed tau. Follow me? Now he draws the same exact bounce diagram, but instead of V prime, it's minus V prime. This is going to be minus V prime. Follow me? Because now the voltage on the line, same magnitude, opposite sign. All right? And then you just draw that, like so. Now, if I want the voltage, say, at the load, and I want to graph it, this is going to be V at the load versus time. I start here because this is where the load is, right? This is Z equals 0, and this is Z equals minus L. I come down here, it's 0 until one time constant, right? And then it goes up at one time constant, whatever the time constant is, I'll just call it TD. And then it goes up to what? Not V prime, but V prime times gamma L plus 1, right? Because V prime gamma L is going to be something, V prime hits, but V prime gamma L is going that way, and they're superimposed at that point. So then I get this, I get V prime 1 plus gamma L right here, and it stays there for how long? Until tau seconds pass, right? And then what happens? Then it goes to 0. Y'all see that? Because when I add this one, this value to this one, this value is going to be minus V prime 1 plus gamma L, right? So it goes to 0. And it's got, this is exactly tau. And then you go down here and bang, bang here, right? Which is what? Well, that's 2 time constants go by. Or now I'm out here at, there'd be a break in this line. Now I'm at 3 TD, where the TD is associated with the time it takes to go down the line once. And then I have the same thing, only now what happens? Now the value here, remember it was 0, right? So now I'm going to have gamma L times V prime times gamma S, right? And then it's going to be times 1 plus gamma L. So then right here, it goes to V prime, and it's going to be gamma L, gamma S. And then at this point right here, it's the superposition of the incoming, which is gamma L, gamma S, V prime, and the outgoing, which is going to be the gamma L squared, gamma S, V prime. So I just put 1 plus gamma L here. Follow me? And it's going to, how long is it going to stay on? Exactly tau, right? That's what he's trying to show you in the book.
Okay.
I think he gets it at the low, but I don't remember.
Yeah, I mean, I was just wondering, because he had it like, the voltages like canceling out.
They do, right? For this part, for this part. But not right here, they don't. There's that time when it's on. And really what it looks like is just a square, it looks like a finite duration pulse just banging down this way. The whole way. That's all it is.
Okay.
All right, so really you can just do one of them. Take the first one, just take V prime, positive V prime pulse, trace it out, and then whenever it goes positive at that end, just leave it positive for tau seconds to kill it. And then go to the next one, leave it positive for tau seconds to kill it. All right? Any other questions about homework or anything we covered? By the way, this is kind of an interesting problem, and I'll tell you why. You know, when you talk about digital communications or digital signal processing, anything at short distances, like on chip or on board, they don't FM modulate that. What they just do is send out simple voltages, all right, that are like 0 to 3.3 volts type voltages down the line, and they are square waves. They're just like that. They usually have a clock, a regular clock that goes from 0 to maybe 5 volts that's transmitted all over the chip. Then they're going to have information that are in a pulse form like this a lot of times. And most of the time, on a chip, most of the time, they're not transmission lines. What they really are, they just look like pieces of wire connecting things. Because they're so short, they're at the frequency of operation, they're much less than a wavelength. But when you deal with digital communications at distances, like if I'm communicating to Shelby and I'm doing something digital, then they don't just send square waves and stuff like this. They don't send voltages that are just nice square things. They take that voltage and have it modulate something in like a transmitter frequency where it's frequency modulated, FM, and send it. And then they have to demodulate it at the other end, because a simple pulse, a square pulse like that sent over a distance, it's going to attenuate and it's going to get corrupted. Typically. Any other questions? All right, today I want to do one. I'm going to go through the finite wire example, straight wire with a charge density. Then I'm going to do the loop. I'm going to do the sheet. And I'm going to also introduce the concept of voltage. But first, let me just do this. I thought about this last night. I wanted to make sure we did this right. Suppose I have a finite length line, and say the upper height is, call it L1, and the lower height is L2. So whatever these values are, it doesn't matter. And say this line has a charge density of rho L. Now it doesn't have to be a constant, but I'm going to make it a constant for this example. It could be something that's a function of height. Call this the z-axis, all right? And I'm just going to call this the rho axis this way. And I want to know what the electric field is at this point. Now, I did this last time, and unfortunately, I didn't do the integration, but I'm gonna do it this time, all right? So, what typically is done, rho is gonna be a distance. Matter of fact, let me just call this D, so you'll know in your mind you're thinking constant distance. And I wanna know what the E field is out here. And I'm gonna say this is right at 0, 2. We could locate it somewhere else, but it serves no benefit. We're gonna just say it's at 0. So now what I'm gonna do is this. I'm gonna take a differential chunk of charge here. My dq, differential chunk, would be equal to rho L, whatever rho L is, it's constant in this case, and it would be times the differential dz. Does everybody understand that? Now this looks like a simple point charge, doesn't it? Right. Now I come down and I say that the differential electric field at this point, here this would be my r distance, right here. The differential electric field here would be equal to dq over 4 pi epsilon naught. Then it would be magnitude of r squared times ar. And I'm gonna do, that's the differential electric field. To get the total electric field, we'd have to integrate. So here we go. We come up here and we say that now the differential electric field here would be equal to, and it's gonna be dq, which is rho L dz, over 4 pi epsilon naught, and then we have r squared. Well, my vector r, this is gonna be a height z, my vector r would be, if you look at this, it's gonna be plus, it's d really, a rho, because that would be the a rho direction, and it's gonna be minus z a z. Just take a moment, make sure you see that that is the radial distance from this point to this point, the vector distance, right? It's coordinates of the point of observation. Well, you can forget about phi, because anytime you have something on the z-axis, phi loses its meaning. All right, so it's all radially away. Take the coordinates here of the point of observation, which would be d minus 0, a rho, and it would be 0 minus z, a z, correct? With me? So now the magnitude of, the magnitude of r is just equal to the square root of d squared plus z squared. And if I square it, I get d squared plus z squared here, because that's the r magnitude squared. And now I need ar. And do you remember how we get vector ar? What do? AR is what? AR is a unit vector in the direction of r, right? So that's always going to be r vector over magnitude of r, right? Well, r vector is right here, divided by magnitude of r. If you notice, the magnitude of r is the square root of d squared plus z squared. So I can just put this d squared plus z squared to the 3/2 power, and then I can make this d a rho minus z a z. Y'all see that, class? And then I can say, therefore, the E field would be equal to, I'm going to take the constants out in front, rho L over 4 pi epsilon naught come out in front. And then I have this. Now I have the integration. Now the first integration will be, I can take the d out in front of it. It would be in the a rho direction. It would be dz a rho over d squared plus z squared to the 3/2 power. And it would go from, here z goes from L2 to L1. It's that. And it's going to be minus, and then it's going to be the integral from L2 to L1 of z az dz over the quantity d squared plus z squared to the 3/2 power. Everybody with me on this so far? Right? Now, the first integral I'm going to do is this one. So if I look at this, what I really need to solve is the integral of dz over b squared plus z squared to the 3/2 power. And that's gonna go from L1 to L2. And here's what I'm gonna do now. I'm going to draw a couple of angles. I'm gonna call this theta 1 and this theta 2. Actually, this is just theta, and up here, this will be theta 2 all the way here. So I'm associate, how about make this theta 1 and this theta 2? What I'm trying to say is now I'm going to introduce an angular measurement. When I'm looking at the point z, it's just associated with theta. When I'm looking at the height of that, the angle here is going to be theta 1 with respect to the actual perpendicular and the vector r. And theta 2 is a measurement from the perpendicular to this vector r here, which is shown. Some of you remember this. This one, the trick we do is we make z equal to d times the tangent of theta. And therefore dz here would be d times secant squared theta. dz would be that. Now, when I look at this integration here would be the integral from L1 to L2, and I'll get the angles in a second. dz is going to be d times secant squared, it's d theta, by the way. D times secant squared theta d theta over, now here I'm going to have d squared plus z squared, so I can actually take the d squared out there, and then I have tangent squared theta plus 1 to the 3/2 power. I replace dz with this. I replace d squared plus z squared, factored out the d squared here, and I have tangent theta, since z is d tan theta, z squared is going to be d squared tangent theta, so I factored out the d squared there. And now, you remember the identity tangent squared plus 1 equals, y'all remember the identity sine squared plus cosine squared equal 1, right? Well, tangent squared plus 1 equals secant squared. Does anybody recall that at all? One person, yeah. So it's tangent squared plus 1 is secant squared. So that means now I have this. I have the integral of secant squared theta d theta over, and I have d squared to the 3/2 is d cubed. So I have 1 over d squared here. Times divided by secant cubed theta. And really now the L1 makes no sense. I translate that into the angles, and it goes from theta 2 to theta 1. And here, y'all see I got a secant squared and I got a secant cubed here. I won't be expecting you to do this. I felt a little bad that I didn't do this last time. I'm just finishing it up. So that's really going to be what? 1 over secant squared, right? Do you remember what 1 over secant is? Well, what did you remember? You had sine, cosine, right? Tan, cotan. Secant is 1 over cosine. Cosecant is 1 over sine, right? So this is really, since it's 1 over secant, it's simply cosine, isn't it? Sure. So this is going to be 1 over d squared times the integral from theta 2 to theta 1 of cosine theta d theta. And that one right there comes out to 1 over d squared. Well, the integral of a cosine is what? Sine, so it's going to be simply the sine of theta 1 minus the sine of theta 2. And that's what you put back in for here. And then you get E, I'll just say this right. E is equal to rho L over 4 pi epsilon naught. Now the D here cancels one of those D squared, so now it's 1 over D. And it's just going to be times sine of theta 1 minus sine of theta 2. I gotta say one other thing too. These angles in this direction are considered negative. These angles are considered positive. And because of that, if you listen to me, remember sine is an odd function. We talked about that, I think, didn't we? So that means sine of a negative angle is actually, or minus the sine of, say, minus A is equal to sine of plus A. So what you can do here, if the angles are strict measurements positive, you can do that. And now you can say that theta 2 is between 0 and 90 degrees, and theta 1 is between 0 and 90 degrees. And this would be the value of that integration. And you can make this a plus in that case. That's 1 over d here. Now this integration right here, if you look at this where I have, I'll do it over here. I'm not going to spend much more time on this, but I want to do this for completeness. Well, here I have the kernel of that integration is really going to be the integral of z dz over d squared plus z squared to the 3/2 power, right? This one you can just do a u, this is going to be from L1 to L2. Here you can say u is equal to d squared plus z squared, and therefore you can put u squared if you want. Therefore du is equal to simply 2z dz. And again, when you're doing this, remember, because you said is d squared plus z squared, when you put, since z goes to L1 right here, this bottom limit would then be d squared plus L1 squared, and the second limit would be d squared plus L2 squared. Do you all see that right there? Right? Now when you do this integration or do this little change of variables, what do you end up getting? Well, z dz would be du, right, over 2. That's z dz would be du over 2. And then it's divided by 1 over, and then it would be u right there to the 3/2 power. Do you all see that, class? Remember, I don't expect you to replicate this or do something that complicated. Just appreciate how you would do it. Now, when you take a look at this, this is from really, I'm just going to leave it as, I'll call this u1 to u2 because we can do the change in a second. So if I have the integral of u to the minus 3/2 power du, that goes to what? That's 1 over 1 minus 3/2, right? And then it's going to be u to the minus 3/2 plus 1, or to the minus 1/2 power, correct, class? With me on that? And then you evaluate it. So this is really going to be, the whole integration comes down to 1 minus 3/2 is going to be a minus 1 over minus 1/2, or minus 2, it's minus 2, and then it's going to be times divided by u, which is d squared plus z squared here, and it's going to be to the 1/2 power, and then you would do the evaluation from L1 to, or really u1 to u2, and plug it in there. Now, the truth is this. Usually, for all the things we do, we set L1 equal to L2. Almost always that's the case. In other words, they're finite wires and we want the E field right off the center point. Doesn't have to be. It could be skewed. So normally this part goes away and you're left with this. And I think in his book, he has that. And I want you to notice one other thing about this. This is my real point about doing this. Now this is true, and this is the field in the arrow direction, right? Do you all agree with that? Now what happens when these angles go to 90 degrees? When theta 1 and theta 2 go to 90 degrees, what am I really talking about? I'm talking a wire that's infinitely long, am I not, class? Well, what happens here? Then E field, for z going to infinity, the E field would be rho L over, and then there's a pi epsilon, but take a look at this. Then I have, and a d, the distance from the axis to the point of observation. Well, sine of 90 is 1, sine of 90 is 1, so I have 1 plus 1, or 2, divided by 4, or I have 2 pi, and it would be in the arrow direction, and that's how we get it for the infinite line charge. Right? That's the equation that is true for the infinite line charge. It's proportional to the charge divided by 2 pi epsilon naught, and d is really the radial distance rho, right? Okay, wanted to do that. But that's how you do that. I don't think he does this one in Dr. Wentworth's book, he just gives the answer. A lot of times they'll work it out. All right, now, next thing we're gonna do is find the electric field from a loop. And I want you to just appreciate this. When we do the electric field from all these basic structures, like an infinite line or a loop, and we get the electric field, you can use that as the building block, as a differential electric field for something like a coil or something with a surface of charge. All right? And I'll show you how to do this. These are all real important because they occur all the time, and they can be used as the building block differential. That little loop will give us a differential electric field instead of the electric field, and it can be integrated up and down a pipe or something. But first, if this is X, this is Y, and this is Z, we're gonna put a loop that's gonna be concentric about the Z axis. In other words, it's gonna be located so the center of the loop is piercing the Z axis right at X, or right at Z equals 0. So we're gonna have a loop like this.
Much of a loop.
It's a loop of wire, and the loop has a radius A. You can give it any value you want. And the loop has a constant charge density of rho L on it. Y'all appreciate this? Now, if we take a look at this loop, it makes sense to do this problem in cylindrical coordinates, doesn't it? It's symmetric about the Z-axis, that's cylindrical symmetry, right? Now what you do is take a differential amount of charge. So come out here and take a differential amount of charge, my dq here. My dq would be charge density rho L times this differential length, right? Now take note of this. When we're in cylindrical coordinates, and this is distance A, this differential length right here is equal to, differential length would be equal to A, right, times d phi. You see what I'm saying? It's the tip of the wiper arm. Think of a windshield wiper. How far does the tip of that blade travel? Well, it's proportional to the length of the wiper times the differential angle, the small angle. Are you with me, class? So that's the differential length. That means dq is rho L times the differential length, or A d phi. There's my differential charge. Now I have to draw a vector to a point of observation. I'm after the electric field on the Z-axis, so I'm at a height Z. And I want to know what this differential field is. Differential electric field here from this. Well, you draw a vector from here to here. I hope your drawing's a little bit better than mine. And I can see that it should look like this, the differential electric field. Can everybody see this, class? Now this is important. What is this vector right here? What is this R in cylindrical coordinates? How do we always get the distance? We take what? The points of observation, right? Minus the points where the charge is. It's causing that field. So if we start with the radial distance, what's R here, or rho here? 0. It's 0 minus, what's rho here? A, right? So it's minus A rho. Now here's something I'm going to tell you. This problem, I'm going to just make this case so I could do this in Cartesian coordinates and you'd see the exactness of it. But does everybody see that if I go directly across the center, I'm going to have another differential charge that's going to have the same exact magnitude as that differential charge? You all see this? And it would cause an electric field just like this one, same magnitude, but such that the horizontal components will cancel. Do y'all see that, class? Can y'all imagine that? And that is true. They will cancel, and that's the reason we're not talking about the A phi term at all. That one's, this is going to have no meaning to us. Are you with me? As a matter of fact, we don't have to talk about the A, I'm sorry, this is gonna have, you don't have to talk about the A phi component here. Let me just get to this R vector. But now in the Z direction, what does it have? I'm sorry, I'm getting ahead of myself. It's gonna be what? Z coordinate here is what? It's just Z, right? Minus Z coordinate here? So it's just gonna be Z, A, Z. And that would be R vector. I'll talk about this axis, this symmetry argument in a second. So now I set up the differential electric field. All of these, the differential electric field will always be expressed as the charge density dq over 4 pi epsilon naught magnitude of r squared ar. Well, for my case, since I'm in cylindrical coordinates, dq is rho L A d phi, right? It's divided by 4 pi epsilon naught, and now magnitude of r squared would be what? Take a look there. Well, the magnitude of r is simply what, guys? A squared plus z squared, right? Isn't that right? A squared plus z squared, correct, class? All right, come over here. By squared, it's just a squared plus z squared. Now I need that vector direction AR, unit vector. What is my AR in this case? It's R vector over R magnitude, correct, class? Isn't that right? Well, R vector is this, and R magnitude is this, and you'll notice I have D squared plus Z, or A squared plus Z squared here ready, right? And if I take that and add in another half power, that makes this to the 3/2 power, and then I have minus A rho plus Z. That's the differential electric field. You'll notice the integration is d phi. To get the total electric field, I would integrate this. I would say that E total, or E on the Z-axis, would be equal to rho L A over 4 pi epsilon naught. And then I would have the integration of minus A rho d phi, right, over A squared plus Z squared to the 3/2 power. And it's going to be plus the integral of Z A Z d phi over A squared plus Z squared to the 3/2 power. And I'm going to mention one thing. Both of these integrations are in phi. Remember, phi is this measurement, right? It's from the x-axis to the actual, in the xy plane to the point you're at, right? Well, how far do we go if we're going to integrate around the whole loop? From phi equals where to where? 0 to 2 pi, all the way around. So this goes from 0 to 2 pi, right? This goes from 0 to 2 pi. And that's it. Now, before I do the integrations, I gotta make mention of something. And this is a mistake people will make. They look here and they say, well, this one will have an A rho coming out, and an A, those are constants, and a minus sign. Then I'd integrate d phi from 0 to 2 pi would be 2 pi, wouldn't it? Here's the problem with this. That A rho is actually, if you think about the Cartesian coordinates, I'll just try to show you this. If this is x and this is y, and I'm at a point here, square root of x squared plus y squared, which would be rho, and my A rho here is in this direction. Do you agree with that? If that's the point. Well, if I move, increase the angle and I come here, you can see that A rho here is pointing in a different direction, even though theoretically it's still in the A rho direction, right? But the angle has changed at theta. Do you all see that? At phi. So what we have to do for this particular problem, because you're right on, anytime you've got charge on the z-axis and you want to find out what the electric field is on the z-axis, if you had a charge density that was not constant, was a function of phi, then what you have to do is break A rho down into, take a look at what A rho actually is. Isn't it going to be AX, right? AX would be equal to this is one here, that would be one times, this would be cosine of theta ax plus the sine, not theta, phi, plus sine of phi ay. So this is gonna be cosine of phi ax plus the sine of phi ay. Do y'all agree with that, class? Remember, A rho is a radial, but not, this is what you have to do this correctly. Now, when I look at this integration right here, just bear with me for a second. That a squared plus z squared does not change versus phi, does it? That's a constant. Do you agree with me? We're at a constant height c. When I integrate a rho d phi, what I'm really integrating is cosine phi plus a sine phi. Do you agree? Well, what happens when you integrate a cosine or a sine from 0 to 2 pi? What do you get? Does everybody agree with that? The area above the curve is the same as the area below the curve, or below, excuse me, the 0 point, and it's 0. And that's why, if the rho L is constant, this term goes away completely. Now, Dr. Whitmore's book makes arguments of symmetry, and he says if we go to a conjugate point straight through the axis, we can see another differential charge that'll cause the same electric field strength, only this angle and this angle will be the same, the horizontal components will cancel, and we're only left with a z component. That's what's in his book if you read it. But this is the formal reason for it, if you go in, if the charge density is constant. If the charge density isn't constant, then you do have both an x and a y component. Do you follow me on that? And that's a more difficult problem. Anyway, getting back to this, now when we do this integration, what do you see happening here? I have EZ equals, it would be a rho L A over 4 pi, right? Epsilon naught. But take a look at this. What happens when we integrate this? I'm going to put a z here. The z appears here. Well, this a squared plus z squared to the 3 halves, it doesn't change. That's a constant. Then I got d phi from 0 to 2 pi, right? Integrate d phi, I get phi from evaluated from 0 to 2 pi is just 2 pi. So then I have 2 pi. And it is in the AZ direction. I've got to make note of a couple things here. So if I cancel the 2 pi's, 2 pi on top and bottom, then I get E on the z-axis is equal to rho L times A times Z over 2, right? Epsilon naught. And then it's A squared plus Z squared to the 3 halves power. And it's in the AZ direction. That's unit vector AZ. That's the E field on the Z-axis. Now, there's something I got to show you about this. I know this can be boring, but just hang in there. You've been there with me for about 55 minutes, so please hang in here. If you look at that, what is the value at Z equals 0?
0.
Can everybody see it's 0 because the Z is here, right? If Z is 0, it is 0. It means the electric field at the origin is 0, and it should make sense because it would only have a radial component, which is 0, right? The electric field as you're going to infinity, as Z goes to infinity, is what? Take a look. Well, I have a Z upstairs, right? As Z's going to infinity, it would be much larger than A squared, right? So I have Z squared to the 3 halves power, or Z cubed, right? And I have Z on top, so it's 1 over Z. Do y'all see this? The E field is falling off like 1 over Z, and as Z goes to infinity, it goes to 0. And this is something you always check anytime you have a finite amount of charge, and this is a finite amount of charge. As you go to a radial distance of infinity in any direction of the z-axis is fine, the electric field has to start falling off as 1 over the distance squared. Just like a point charge. A point charge, the electric field falls off as what? Q over 4 pi epsilon naught R squared. Follow me? And it does, in fact. The E field falls off as 1 over Z squared, which is the radial distance, and it goes to 0. But what happens when Z is negative as far as its orientation? When I'm above this axis, the E field's pointing this way, isn't it positive? What happens when I'm below? Z is negative here, so it points in the negative direction, which makes sense also, because the electric field should be pointing away from positive charges. So it checks the boxes, that is the right answer. Understand, everyone? Now the next thing we're gonna do is we're gonna do a plane of charge, of constant charge density, and this is important. So we've done a line of charge, you're responsible for knowing these, all right, you gotta know. First we've done a point of charge, then we've done an infinite line of charge, then we've done a loop of constant charge density, the constant charge density along the line, the actual loop. Now we're gonna do a plane. A lot of ways to do this problem. By the way, if I have an infinite plane of charge, how much charge do I have? Is it finite or infinite? Think of the word I said. Infinite plane means infinite amount of charge. That means the E field will not fall off as 1 over z squared from the source, which is very important. It's not going to fall off as 1 over r squared if we have an infinite amount of charge. And there's no such thing as the universe is an infinite amount of charge, or an infinite plane per se. But if I'm real close to this carpet, then, so to speak, it looks infinite to me if I'm looking at it. It looks like an infinite plane. And that's where we use a lot of these formulas, is when we approximate things. We don't have infinite wires anyway. But if I'm 1 inch from a power line that's hanging from a pole that is 30 meters long, then it looks infinite to me there. So I can use a lot of these approximations. And if I've got a constant charge distribution on this carpet and I'm 1 millimeter above it right here, it looks infinite to me. So I can use these approximations to get the feel. Let's do it this way. If we have an infinite sheet of charge, I bet you remember this from physics. How many do? Remember this problem from physics? This is a classic problem. These are ones that the physics professors, they get excited trying to explain how simple it is to do these, usually. Some don't. Ones I had like to do it. So this is x, y, and z, and what we're gonna do is we're gonna put this infinite sheet of charge at really z equals 0, so it's in the xy plane. It's just an infinite sheet. Now work with me here on this one. So if we've got an infinite sheet of charge, not drawn very well, I'm doing my best. Infinite sheet of charge, the one way to do this, if you can imagine this for a second. What if I take, I can assume this, I can break this thing up into little strips. I'm gonna say this is a differential strip that actually goes on to infinity. And the thing has a distance dx here, right? Can you all see what I'm up to? So if dx is very small, it looks like a line of charge, and the effective charge density, or charge per unit length, rho L, would be equal to the surface charge density, rho S, times dx. Does that make sense to everybody? Just think, I got a flat little strip of width dx. I've got a surface charge density. Rho S is charge per meter squared. Rho L is charge per meter. And rho V is charge per meter cubed. They're simply charge densities. And you've had these before, I think, in physics, right? Charge densities, any kind of density is always per meter squared, per meter cubed. But if you think about this, rho S is charge per meter squared times dx. Well, dx units are meters, so then I'm left with charge per meter, right? So this is like rho L. So what this looks like is an infinite line of charge at a position, and you can say it's at a position x, where x would be negative here, right? And it's infinite, or I'm sorry, y here. This is not dx, I'm sorry, I should call this dy. My bad. It's dy, it's up and down the x-axis. So let me try to now put this problem in a form that you'll appreciate. So now what I'm going to do is cut this plane in half at x equals 0, and I'm just going to look at this. This is my y-axis. Here's z, and now I've got this little chunk I've got an infinite line of charge density where my rho L is now equal to rho S dy right here. And now I have a differential electric field right here. I have dE here, and that would be equal to think of it this way. Remember, if you had an infinite line charge with rho L on it, right? And I'm a distance rho away, the electric field here, E, would be in the rho direction, and it would be equal to simply rho L over 2 pi epsilon naught rho, right? It's in the A rho direction. You with me, class? That's if it's an infinite line, correct? So what I can do is, here's my infinite line. It's coming out of the board, or out of this whiteboard. It's got this value. That means this differential electric field will have that form. It's rho L, or rho S dy, over 2 pi epsilon naught. And now I need this distance. So I'm gonna say this is at a height z. This distance, I'll just leave it as y. So this distance here would be the square root of z squared plus y squared, right? With me? Now it's going to be divided by that, which is going to be z squared plus y squared to the 1/2 power. And it's in a direction, and actually I better put a vector there. So my vector r here, or rho, would be equal to, well, if I go from here to here, both z and y are positive, so it's going to be y ay plus z az. And then for the unit vector business, when I get r vector divided by magnitude of r, that would be equal to y ay plus z az over the square root of y squared plus z squared. And that would be my AR, or it's my A rho really. And that's the A rho here. So that means I can make this just to the first power, and then I have y ay plus z az. You with me? What I've done is a building block approach. I used my knowledge of an infinite line charge to get the electric field from a differentially thick line charge. It's infinite. So that's the electric field, differential electric field. Now the total electric field, I'll just tell you this. The total electric field, I'll put it down here. Well, I'll do this. The total electric field will just be what? The integral of this, you remember it's dy, but it would be from minus infinity to infinity. Wouldn't that be equal to the total electric field, class? If you integrated that from y goes from minus infinity to plus infinity, would be the total electric field. Now take a look at this for a second and appreciate what I'm about to show you. Just look at it. What do you see happening with the y component, or the horizontal component? What did you say?
Does it cancel?
Has to cancel. Doesn't this make sense? If I know for this charge, I've got another what? I got a conjugate charge right here that's doing the same thing. It's the same magnitude, right? Only what? The vertical components will add, but the horizontal components will cancel, won't they? We could get in and write the equations formally and do it, but that's what's going to happen. And engineers, good engineers make use, they exploit symmetry. Anytime you can use symmetry to simplify a problem, use it, where you can reduce the level of complexity. So that means the y component I'm not even going to bother with. That goes away. I'm worried about this component. So now I say that the E field will be equal to, the rho s comes here, 2 pi epsilon come out in front, right? And then I have the integral of z dz az here over z squared plus y squared, just to the first power, from z goes from minus infinity to infinity. Do y'all agree with me? That's z going there, correct? Well, how do you do this integral? This is not so bad. You see how I have that z dz? That gives me a lot of confidence this is an easy one to do. If I make u equal z squared plus y squared, or you could, better yet, you can make u squared equal to z squared plus y squared, right? Then du would be equal to, or 2u du would be equal to 2y dy. And here z is a constant. Remember, z is just the position above the plane that I'm observing the E field. It does not vary. You follow me on this, class? So if that's the case, that means 2u du equals 2y dy, or u du is y dy, and that means this integration right here, I can render as z is a constant. I can say that the E field is equal to rho s over 2 pi epsilon naught, and then I have the z can come out in front, and I have really it's going to be just 1 over u squared. Wait a second. That's a dy integration, not dz. That's the problem. That's a dy. And that z. That won't actually work. Then I have 1 over z squared plus y squared. And it's dy. And that gives me rho s over 2 epsilon naught az. There's az here. And that will be the answer. I didn't do the integration on this one because it's actually a dy over that. And that means I gotta do that trig thing again. Well, I'll have, I would have y equal to z tan theta, and I have to go through that business again, but this would be the answer. It's rho s over 2 epsilon naught az. Do you see that in his book?
Yeah,
What page is that on?
I think it's 140.
And when he did that integration, did he get a tangent? Or maybe he didn't do it.
Oh, yeah, that's 141, and yeah, he got a tangent.
And it's
Inverse
tangent, and he's got where the tangent angle goes from minus pi over 2 to plus pi over 2, or minus 90 to plus 90.
I mean, he has inverse tan of y rage from negative infinity to infinity.
Yeah, and I'm sorry, inverse tan to that. When you do it, this is what you get, and I'm going to make a point about this. This is not AZ. Don't put AZ here. Put a normal. Let me make this clear. A normal vector is something that is perpendicular to the plane you're talking about, and it's in a direction away from the plane. Now, I have to say this for a reason. Make sure you put a normal there. So, let me recreate this field of the problem. Suppose I have an infinite plane, but I'm going to look at it just down an edge, and this plane has a value of rho s on it. Now, if I'm above the plane here, a normal is in this direction. And that would be the z-axis here, plus z. A normal would be plus az. But if I'm below it, a normal here is minus az. You all see this? It points away from the plane. Now, if there's a charge density rho s here, it means the electric field above it, wherever in this region here, the E field would be equal to rho s over 2 epsilon naught positive az. And down here, the electric field, same magnitude, only minus rho s over 2 epsilon naught az. You'll notice one thing about the electric field from an infinite plane of charge, and this should make sense to you. Do you see how it's not a function of how high above the plane you are? It's not a function of z, is it? That should make sense. If the plane's infinite, if I go up 100 feet and I look to the edge, it's still out there at from 0 to 90 degree swath right there, right? If I look at the other edge, it's still, I have to go to from 0 to 90 degrees to look at that horizon, right? If I go up a mile, it's still the same. It always looks infinite, if it is an infinite plane. That means the electric field should not be a function of distance, above or below. And it's not, except for one thing. The sign does change if you're below it. And remember this, the electric field always points away from positive charge sources and towards negative charge sources. Okay? All right, so that's basically the electric field from the ring, or from the loop, from the plane, and from the line. Those are the three things you have to know for the infinite ones, all right? And also how to write the electric field in terms of a differential electric field from a differential amount of charge and then integrate it, okay? I'll never expect you to do difficult integrals, but I do expect you to understand the basics well. And I'd give you, if there was a difficult integral that appeared, I'd give you that form. I'd give you the solution. And actually, most of your calculators, I think, do symbolic integration, don't they? If you have a TI 89 or TI 93, they do symbolic integration, right? Which is a real benefit, because that means any of these integrals becomes trivial. They'll do them for you. And if they're actually, if they have not indefinite but definite bounds, they'll give you a numerical answer. Did anybody see if your calculators have epsilon naught, mu naught, c in them? It's constant. What's that?
I couldn't find it.
You don't have it? What do you have? An
It's
89?
89, unless I might not know where it is though.
A lot of these calculators, don't you have memory cards you can put in there? You can get a scientific memory card and you'll have all these constants available to you, but I'm not sure. See, the problem is you're gonna have like a two-function key to get them. It's not gonna be, it's like a shift something to get it. It's not just there as an icon. At least not the ones I've seen. Okay, now we're gonna get into something that's, in the book he calls it voltage, as a matter of fact. We just got through these charge distributions. I didn't do spherical coordinates yet for a reason. We don't need them yet. And I'm not even gonna bother with the volume charge, but the electric field from a volume charge is the differential amount of charge from a differential volume of charge, and you integrate it over the whole volume. But that, he does, actually he does flux next. We'll do flux, but I wanted to get to voltage. I'm not gonna have time to. Let me just talk about this. This is electric flux. I wanted to do voltage. I don't have time for it now. Give me another minute and I'll let you go. So when we talk about electric flux, I gotta understand what flux is. Flux has to do with some vector field quantity penetrating a surface. For instance, when I take a look at water flowing, I have so many maybe cubic feet per minute flow rate in a certain direction. All right, that is a density. If I wanted to know how much water passes a surface, a finite area, that would be the flux that penetrates the surface. That's the idea. Flux is how much of a vector quantity penetrates a surface. So what we do in electromagnetics, the thing we talk about when we talk about electric flux is the D field. And the D field is actually equal to epsilon naught times the E field, which makes it nice. The D field is actually in terms of the units of the D field are coulombs per meter squared. So the units are charge. It's Q over meter squared. Anytime you see 1 over meter squared, that's a flux. Are you with me? Coulombs per meter squared is a flux. Now here's the deal with this, and this is important. This is a relationship between the E field and D field in free space. But if you take the integral of d dot ds, this is called Gauss's law, and this little symbol here means closed integral, closed surface actually, you end up with the amount of charge inside the region. And this is called Gauss's law. Do you remember Gauss's law? Now, the reason Gauss's law is so interesting and popular is if you can exploit symmetry, you can get these D field values for charge distributions without doing any type of difficult integrations. You don't have to worry about it. I'm going to do one, just show you this, and there we go. Let's do a point charge. If I have a charge Q, right? And I come out a distance R. You all agree with me, I'm sure, that the electric field from that charge should only be a function of the distance R away, correct? So, according to Gauss's law, if I put a Gaussian surface around there and enclose this thing in a sphere, this is the D field. The D field will always point outward. It'll always point radially outward, right? It'll point away from the charge. And if I'm at a given distance R away, would you agree that the magnitude of the D field will be the same all over that surface? So then I can say this, that the integral of D dot ds over that closed surface will be the charge enclosed. Well, the charge enclosed is Q. Since the D field magnitude is a constant, I'll just call it D magnitude there. Now what's the surface of a sphere? What's the equation for surface of a sphere of radius R? 4 pi r squared. You give me volume. This is 4 pi r squared, which means the D field in the radial direction would be Q over 4 pi r squared, right? It would be in the AR direction. And how do I get the E field from that? Well, I divide the D field by epsilon naught and I get the E field. So if I divide by epsilon naught, now I have the E field, and I'll stop there. But I'll show you using Gauss's law, we can get the E field for all the charge distributions except the loop very easily and quickly using Gauss's law. And that's next, and then we'll do voltage on Friday. So the quiz on Friday is going to be, it'll be on electric field problems. It won't be on the bounce diagram. Okay, fair enough. See you Friday. I'll give you some more homework. If you have questions, I'm available now in my office. Anybody have any questions?